The first time you see matrix multiplication, it simply looks mysterious. It looks surprising. It doesn't seem to reflect anything you've ever seen before. And the why it's defined like that and what's the motivation for this weird definition, in fact, is revealed when we'll see what matrices are good for. So this multiplication is in fact going to correspond to exactly what we do when we represent stuff using matrices, like operators and like systems of equations, etc. Okay? So I'm going to start with an example, just so you see what I'm doing, and then I'm going to write the formal definition, which takes time to get used to. So here's an example. I'm going to take the following two matrices. This is going to be A. It's going to be 1, 2, 3, 4, 5, 6. So this is a matrix. We're going to call it A. It's a 3 by 2 matrix. It has 3 rows, 2 columns. Do you agree? And I'm going to multiply it by the matrix negative 1, 0, 1, 1, 2, negative 2. And I just did the ridiculous thing of not leaving enough space, which is really ridiculous. So I'm going to copy it again. Please forgive me, because I need room for the product. So 1, 2, 3, 4, 5, 6. That's A. It's a 3 by 2 matrix multiplied by negative 1, 0, 1, 1, 2, negative 2. This is B, and B is a 2 by 3 matrix. It has 2 rows and 3 columns. What's important, matrix multiplication is going to be defined only when the second index of A, namely the number of columns in the left matrix, equals the first index of B, namely the number of rows in the right matrix in the multiplication. In this example, the 3 and the 3 coincide as well, but that's just coincidental. It doesn't matter. So what is the product? So the product, which we're going to call AB, is going to be a 3 by 3 matrix. The 2's kind of cancel out if you want. So it's going to be a 3 by 3 matrix. So I told you the size. Now all that remains is to tell you what the entries are. Okay? And the entries are calculated as follows. You take the first row of A and multiply it by the first column of B. And how do you do it? Just to trace my hands, you do 1 times negative 1, which is negative 1, plus 2 times 1. Blip, blip. 1 times negative 1 plus 2 times 1. So it's negative 1 plus 2, it's 1. That's the first entry here. Okay? Now let's do the second entry in row 1, column 2. Row 1, column 2 is going to correspond to row 1, column 2. So it's 1 times 0, 0, plus 2 times 2, 4. So this is going to be a 4. The third entry, entry 1, 3, row 1, column 3, corresponds to row 1, column 3. 1 times 1, 1, plus 2 times negative 2, negative 4. 1 minus 4, negative 3. Good? Okay? Starting to get the hang of it. It's weird. It's just weird the first time you see it. Let's do the second row. Second row, first column. Second row, first column. 3 times negative 1, negative 3, plus 4. Negative 3 plus 4, 1. Row 2, column 2. Row 2, column 2. 3 times 0, 0, plus 4 times 2, 8. Try doing it before me. Don't look on the board. Try doing it on your own. See if we get the same stuff. I'll do it a bit slower. Row 2, column 3. Row 2, column 3. 3 times 1, 3, plus 4 times minus 2, minus 8. 3 minus 8, negative 5. Row 3, column 1. Row 3, column 1. Negative 5 plus 6, 1. Row 3, column 2. Row 3, column 2. 0 plus 12. Row 3, column 3, the 3 entry of the product. 5 minus 12, negative 7. That's how you do matrix multiplication. Okay? So row times column gives you the entry corresponding to the row number that you took from the left matrix times the column number that you took from the right matrix. Okay? The only way to get the hang of it is to now take a 5 by 4 matrix and multiply it by a 4 by 6 matrix. You'll get a 5 by 6 matrix. That's a lot of entries to practice on, and just do it. Okay? So, let's write the formal definition. Okay? So the definition of matrix multiplication, which is the weirdest thing you've ever seen, unless you've seen it before. Even then it sometimes looks weird. So, several prerequisites defined for A of size m by n and B of size n by whatever. Let's call it L. So the point is that the number of columns in A has to equal the number of rows in B. That's the only case in terms of sizes where multiplication is defined. The product is a m by L matrix, is C m by L. So the product has as many rows as A and as many columns as B. Okay, that's the product. Now, the big issue is the entries. So the entries of C are, so what is the ijth entry in the matrix C? The ijth entry is what? Let's go back to the example and understand what we did. The ijth entry, let's say the 2, entry, we took the first element in the second row of A times the first element in the second column of B, plus the second element in the second row of A times the second element in the second column of B. And if there were more rows and columns, it would go on, right? So the way to write that is the sum, and sum we write sigma, and don't get afraid. And we're summing, the summation index is going to be k, and k is going to go from 1 to n, where n is this joint index that disappears in the product. That's how many additive factors we're going to have. 1, 2, let's do it right for you. 1, 2, 3, up to n, right? That's the number of factors we have. Do you agree? And what are we summing? We're taking the ith row of A, so the elements in A, we're going to denote them by little a's, with index I for the row, and then we keep varying the index of the column. So that's k. So we first take AI1 and multiply it by B, the bth element, with the same column index as the row index, the same row index as the column index of A, and now J. Okay? So this is really this I think is intimidating the first time you see it, but you should think for a minute, and try to decipher it and see that this is precisely what we did in the example. So this is just writing, this is a summation notation for writing AI1 times B1J. Okay, plus AI2 times B2J, plus dot, 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 all the way up to AIN times BNJ. Okay, so it's not trivial to grasp this the first time you look at it. You have to really see the correspondence between this and what we did in the example. You first have to understand what happened in the example, okay? Do a couple more examples, and then see that this is precisely what happened there, okay? Okay, maybe another way of kind of expressing it, let's do it. So here's a more abstract way of, so here's A, and what we did, here's A, here's B, and we get a matrix C. So this is C and this is B. And in order to get the ijth element in C, so this is the ith row and the jth column in C. So this dude here is the element Cij, little c, ij. What we did is we took the ith row from A, the entire ith row, let's circle it here. This is the entire ith row. Well, didn't draw it in the right place, right? Let's make it more convincing. So we take the entire ith row in A, I is somewhere here, the entire ith row, and the elements of the ith row are what? Are AI1, AI2, AI3, all the way to AIN, and multiply it by the jth column of B. The jth column of B, whose elements are B1J, B2J, big J, sorry, B2, J, B3J, all the way up to BNJ. And we do AI1 times B1J, AI2 times B2J, plus AI3 times B3J, plus AI4 times B4J, dot, 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 all the way up to AIN times BNJ. That's how we get the ijth element sitting here, okay? And what I just said, this summation, this times this plus this times this, is precisely what we wrote on the previous board over here, okay? Look here a second. That's precisely this summation expressed in sigma notation like this. Woo! Okay, you really need to just practice examples and you'll get the hang of it without going to, this is required when you do very formal proofs, and before you try to really grasp this, get the idea of what's going on. And then it's not that difficult. We just drew the picture and it should be pretty convincing. Okay, now I want to make several remarks. So it turns out that matrix multiplication is not what you may think it is. So remarks. AB is not always equal to BA. In fact, it's not even always defined, right? If in order for AB to be defined, the number of columns in A has to equal the number of rows in B. But if you write them the other way, it might not work any longer. Even if it is, the product could be different. So for example, Take very simple 2 by 2 matrices. 1, 1, 1, 1 times 1, 1, negative 1, negative 1. What's the product? So it's 2 by 2. This is A, this is B. Both are 2 by 2. The product is going to be 2 by 2. But in fact, we can write it the other way as well. So let's do both calculations. 1, 1, negative 1 times 1, 1, 1, 1. Let's see what we get. So here we get, tell me if you agree, 1 times 1 plus 1 times negative 1. 1 minus 1, 0. 1 times 1 plus 1 times negative 1, 0. 1 times 1 minus 1, 0. 1 times 1 minus 1, 0. It turns out that these two matrices, their product is 0. But when we do it this way, so this is the matrix AB. It's defined. But this is the matrix BA, in which we get 1 plus 1, 2. 1 plus 1, 2. Negative 1, negative 1, negative 2, and negative 1, negative 1, negative 2. So A and B, A times B and B times A, are both defined, but they're very different. Okay? So here's an operation, operation which we call multiplication, and we'll see why it's a good name for it, but it's no longer commutative. Okay? Multiplying A and B and multiplying B and A, even when both are defined, does not give necessarily the same thing. Okay? So even when, in terms of sizes, it's defined. So in particular, or maybe it's not in particular, it's continuing the same remark, formulas that you're used to, formulas like, for example, A plus B squared equals A squared plus 2AB plus B squared, are not valid any longer. This is not necessarily equals. So I'll add no formulas like this. Why? Because A plus B squared is A squared plus AB plus BA plus B squared. When it was numbers, AB and BA, we just coupled as 2AB, but that's no longer the case because AB and BA could be different things. Okay? Moreover, there could be zero divisors. There could be zero divisors. We mentioned that when we talked about fields. So what are zero divisors? A is not 0. B is not 0. But their product is. That can never happen in numbers. Okay? Or in polynomials or in complex numbers, but it could happen in matrices. Here it is. A is not 0, B is not 0, but their product is the 0 matrix. Okay? No cancellation. No cancellation. Cancellation rules, like if you have AB equals AC, if it were regular numbers, you would say, okay, this implies B equals C. Right? You can cancel both sides by A. No longer the case. Okay? Because AB equals AC only implies that AB minus AC, so this does imply, let's write that, AB equals AC implies that A times, let's write AB minus AC is 0. This is true. And this implies there is going to be a distributive law. We'll say it in a few minutes. AB minus C is 0. All this is true. But this doesn't imply that either A or B minus C is 0. So A could be non-zero and B minus C could be non-zero, meaning that B is not C. Okay? So many things that you're very used to and are very intuitive, and that it's even a drawback because you're used to writing these things. You don't think, right? When you replace a product with a product going the other way, you don't give it a second thought. It's obvious. It's always true. Or when you cancel things like this, AB equals AC, blah, blah, B equals C, can't do that. So you have to be very, very, very careful when working with matrix multiplication. Okay? Anything you want to claim, and we'll do it in a separate clip, we'll list the properties of matrix multiplication and prove a few, and there are going to be some properties. I'm not saying that there are none. For example, associativity holds and distributivity holds, and many things do hold, but you can't take anything for granted. You have to be careful because it's really new territory you're exploring and you don't know where you'll step. You have to be careful. You have to only use things that you've thought of and know are valid, and cannot just work in your, secure intuition-based environment, which is based on numbers, which is just a different thing. Okay. Okay. So in the next clip, we're going to discuss properties of matrix multiplication. What is valid? And after we're done with that, we can finally start exploring what matrices are good for and the relation to the core topics, other core topics in this course.